Hey guys, today we will be looking at a practice problem from Chapter 4, Kinematics in two directions, and specifically focusing on rotational type problems. So the question reads, astronauts use a centrifuge to stimulate the acceleration of a rocket launch. The centrifuge takes 30 seconds to speed up from rest to its top speed of one rotation every 1.3 seconds. The astronaut is strapped into a seat 6 meters away from the axis. So as you can see, I've already listed a couple of the knowns that we know, that the radius is 6 because the astronaut is 6 meters away from the axis, and we know that it started from rest, so the velocity initial is 0. Now, part A asks, what is the astronaut's tangential acceleration during the first 30 seconds? So I've already written down an equation that you guys should have gotten in class, and it's that tangential acceleration is going to be our change in our velocity divided by change in time. Now, an important thing to remember is that our change in velocity is not going to be our change in angular velocity, or omega, but it's a change in our tangential velocity because we are solving for tangential acceleration. So that part's pretty important. And now, so this value right here, the change in velocity tangential, we recognize that our velocity initial was 0, so the only thing that's going to impact it is the velocity final. And how we get the velocity final is, if you guys remember, it's 2 pi r over r period. So that's our equation for tangential velocity. And if you guys solve this out, you guys should get 12 pi over our period, which is also given to us, because our period is the amount of time it takes to make one rotation. So right here it says one rotation every 1.3 seconds. So our period is 1.3 seconds. And now we have our change in velocity. All we have to do is divide it by the time we take. And it says that the centrifuge takes 30 seconds to speed up from rest. So our change in time is 30 seconds. If you solve this out, you should get approximately 29 up here and 30 down here, and that equals 0.97 meters per second squared. It's really important to recognize that this is tangential acceleration, so we're not talking about, or we're not going to use omega, which is going to be our angular velocity, but rather we're going to use our tangential velocity. It just makes it a bit easier. Next, part B reads, how many g's of acceleration does the astronaut experience when the device is rotating at top speed? And it tells us that 1 g is 9.8 meters per second squared. Now, there's two ways to do this, and the first way is just strictly like with the formula, so I'm going to do that one first. And we're going to write out alpha rotational, or the rotational acceleration, also known as centripetal acceleration, which, by the way, centripetal force is imaginary force, you might say, because it doesn't really exist. It's consisted of a bunch of other things. So our rotational acceleration, we know that our rotational acceleration is going to equal our velocity tangential squared divided by our radius. So we already know our velocity tangential from up here, which was 29. So we're going to square 29 and then divide it by our radius, which was 6.0 meters. And you're going to get 140 meters per second squared as your acceleration rotational, which is pretty ridiculous. But we cannot stop there because, remember, it says in terms of g, and it gives us that a g is 9.8. So all we have to do is divide this by 9.8 meters per second squared. The meters per second squared goes away, and we are going to be left with approximately 14.3 g's. That's the first way to do it. Now, the second way to do it involves a formula that we did derive for in class, so maybe you guys remember it, but it goes, rotational acceleration is going to equal our radius multiplied by are so omega squared, or rotational velocity, angular velocity squared, sorry. So omega is angular velocity squared. And if you guys want to see how we derive this equation from a couple of relationships we already know, I'm probably going to be making another video about it. And when I do, I'll leave the link in the description below. Or if you guys really just want me to make it immediately, just comment below. And okay, so we're gonna do this, but we have to remember that first we have to solve for this omega. So if you guys remember, omega equals 2 pi over our period. And over here we know that 2 pi and our period, as stated up here, is 1.3 seconds. So 2 pi over 1.3 seconds, and we're going to square omega. So omega squared multiplied by our radius, which is 6.0 meters, and that will give us a final answer of approximately 139.8 meters per second squared. And once again, we're solving in terms of g, not just our rotational acceleration, so we're going to divide that by 9.8 meters per second squared, and you're going to get approximately 14.3 g's. So that is 2 ways to solve this problem. And a quick thing to remember, so just quick things that this problem does is it will try to catch you off guard, and it will try to see if you use angular velocity instead of the tangential velocity up here when you're solving for tangential acceleration. So be careful of that, and remember that when we're going to be taking tests, or whenever you guys are going to be taking your tests. And good luck. Thanks for watching.